Welcome back, everyone. In the last few lectures, we were doing a review of linear algebra. In the last lecture, we did this systematic method of solving linear systems of equations. That's the Gauss-Jordan elimination algorithm. I was slightly imprecise the last time. So the aim is to take a matrix, the so-called augmented matrix. The actual aim is to solve the system of equations. This column vector is irrelevant, so you just put these coefficients on the right-hand sides into a matrix. That's the so-called augmented matrix. And you do these so-called row operations. By row operations, I mean interchanging rows or multiplying a row by a non-zero scalar, or adding a row to a multiple of another row. Right? This can be zero also, of course. Using these row operations, we want to bring it to a standard form. So the row echelon form is the following, that if you take the first non-zero entry of any row, that's typically called a pivot of that row, then below the pivot you must have zeros, and you must have zeros to the left of the pivot as well in the other rows. That is, the pivot in the next row comes to the right of the pivot of the previous row. This is the row echelon form. For row reduced echelon form, it's almost the same thing, except first of all these pivots have to be normalized to 1. Secondly, in the row echelon form, these can be non-zero. That is, the entries above the pivot can be non-zero, but here even the entries above the pivot as well as below the pivot must be 0. Yeah. So recall the algorithm was as follows. You interchange rows enough number of times so that the first row has a pivot which is on the leftmost side, right? And if you have more than one row having a pivot, like for example, say for instance, you have this matrix, let's say right? You can interchange the first and the second row to make it this, right? But so the point is, you could have done it with a third row as well, right? There is nothing stopping us from doing that. So what interchange must you do? That really depends on the situation. Sometimes it's good to interchange rows so that the pivot in the first row is a number that's neither too large nor too small, because you want to divide by it, right? So on computers, if you divide by things that are too small or too large, you can have problems. Right. So that's one thing, and then what you do is you clear everything below this by means of row operations. So you get something like this and something, right? This is not yet in the row echelon form. I mean, for one thing, you would need to normalize this. But the one above this is not 0, so you have to further clear that as well. Okay, so and you have to clear the thing below as well. Okay, so I'll give you a concrete example, but that was just one little point I didn't mention clearly the last time, that for the row reduced echelon form, not only do you want these pivots to be 1, but also things above the pivots to be 0. Okay, so let's do a concrete example. Let's aim at solving this system of equations. X minus 2y plus z is 5. and x minus 4y plus 6z is 10. Okay? So the way you would do it is you would create this matrix of coefficients. You would also write the right-hand side, so you'll get this. Right. So the first order of business is we don't have to interchange any rows here because the pivots are all in the first column for each row. Yeah. Well, so we must normalize this. So when you divide by 2, you'll get 1 minus 5 divided by 2 minus 3 divided by 2. We'll keep the others as they are. I'm not strictly following the Gauss-Jordan algorithm, but a slight variant of it. I mean, you can use your common sense basically. Just use row operations to get it to the row echelon form. The next order of business is to make sure that these two become 0, right? So if you take the second row goes to the second row minus the first row, yeah, what will you get? You'll get 1, you'll keep the first row as it is, the third row as it is, the second row is this, minus 2 plus 2.5 is 0.5, and then you'll get minus 1 and 5 and 13 divided by 2, right? Because 5 plus 1.5 is 6.5. Then you clear this one as well. So you can try the third row goes to third row minus the first row, and you'll end up with this matrix. Right. Now you play the same game for the smaller matrix. Okay. So again, one of these must be normalized to 1, right? So for example, you can take the second row and scale it up by 2. So you won't be changing the first row at all. 13 and this. And then, as usual, you clear the thing below it, right? You also clear the entry above it. So basically, R3 the third row goes to third row plus 3 by 2 times the second row, so as to clear this one. And the first row must also be changed so that you clear this one, right? So you get 0, minus 3, 31, minus 2, 13, 0, 0, row 31. This is in the row echelon form. It's not yet in the row reduced echelon form. By the way, why do we care about row reduced echelon form? Because the theorem of Gauss and Jordan is that the row reduced echelon form is unique. Okay. If you don't demand row reduced echelon form and only say row echelon form, it's not unique. Now this is not in the row reduced echelon form, but we don't care. At this point we can actually solve the equation. If you rewrite this in terms of an equation, you'll say 0 times x plus 0 times y plus 1 times z is 31. So z is 31. Likewise, this is 0 times x, 1 times y, minus 2 times z is 13. So you substitute z equals 31 here, and you can solve for y, and so on. Likewise, you can solve for x as 124 from this equation. Yeah. So this is an example of how you would use the Gauss-Jordan elimination in practice. Okay. So this is not just a mere academic exercise just to recall what Gauss-Jordan elimination is. We will have occasion to employ it. So that's the point. Okay. All right. So now we know a systematic way of solving equations using matrices. We know what matrix multiplication is. Rather, we already know these. We've recalled these things. We need some more things from linear algebra. So suppose you have a matrix A. You have the rows of the matrix. These rows are vectors, right? I mean, suppose this is an m by n matrix, which means you have m rows and n columns, right? So there are n entries in each row. So these rows are all vectors in Rn. There are m of these vectors in Rn, yeah? Now the point is, these vectors, so the linear span of the rows, what exactly is the linear span again? It's the smallest vector space within Rn that contains these. In other words, more simply, you take all possible linear combinations of these rows, like C1 times the first row plus C2 times the second row, etc. For all possible linear combinations, this set is a subspace of Rn. This subspace, recall, is called the row space of the matrix. Likewise, you can also take the columns. How many entries are there? There are m entries in each column. And there are n of these, so these are all vectors in Rm. And likewise, you can take the span of all these columns and you get the so-called column space of A, which is in a different vector space. In Rm, this is in Rn. Now, the dimension of the row space of A miraculously turns out to be equal to the dimension of the column space. It's not at all obvious that this must happen. Of A. These numbers are called the rank of the matrix. This would have been called the row rank and this would have been called the column rank, but since they're equal, we simply refer to these numbers as the rank of the matrix. Yeah. So for example, if we go back here, let's look at, let's say, this matrix. What do you think the rank of this matrix is, right? So think about it. You can pause the video and think about it. The point is, the row space is spanned by these vectors. These vectors are linearly independent. Why are they linearly independent? If you take a linear combination, let's say C1 times the first row, C2 times the second row, C3 times the third row, automatically if this is 0 if and only if C1 is 0 and C2 is 0, and hence C3 must also be 0. Yeah? So in other words, the rank of this matrix is 3. Now herein lies the utility of the Gauss-Jordan elimination algorithm. The point is, these row operations do not change the row rank of the matrix, or in other words, the rank of the matrix, right? Why do they not change the rank of the matrix? First of all, these row operations are linear operations, right? All the row operations are obtained by simply taking a linear combination of these rows, okay? Secondly, these row operations are invertible. You can reverse this one, right? You can simply multiply by twice times R1 to get this back, and likewise, okay? So in other words, you have a bunch of linear maps, that is, you're taking linear combinations and you can reverse them. Therefore, this does not change the rank. In other words, the rank of this matrix is exactly the same as the rank of this matrix, which is 3. So how do you find the rank of a matrix? You bring it to the row echelon form or row reduced echelon form, which would make it even clearer, right? When you bring it to the row reduced echelon form, the row reduced echelon form is typically of this type, where the last few rows only have zeros and the others have things that are not necessarily 0, right? And so on. So what is the rank of the matrix? You can easily read off the rank from the row echelon form. It's simply this number of rows. In other words, if you take the last few rows that contain only zeros and subtract it from the total number of rows, that is the rank of the matrix. Why is that so? Please think about it. It's for the same reason as this. Yeah. Okay. So the row reduced echelon form is useful for calculating the rank of a matrix. Now, obviously, the rank of an m by n matrix is less than the minimum of m and n. Why? Because the rank, the row rank and the column rank are the same. The row rank is the dimension of the row space, and if you have m vectors and you take their linear combination, the maximum dimension you can get is m. The best thing possible is all these vectors are linearly independent. The only other possibilities would involve linear relations between these vectors, so that would only reduce the dimension. Yeah? So it's less than the minimum of m and n. If the rank is indeed one of these equal to this, that is, if it is the maximum possible number it can be, then the matrix is said to be of full rank. Very suggestive terminology, nothing mysterious about the terminology. Yeah? Okay, now herein lies an important theorem. A matrix is invertible, a square matrix, n by n matrix is invertible if and only if it is of full rank. Why is this so? Well, it's not very difficult to see. What does invertible mean? There exists another matrix so that AB is identity. In other words, you must be able to solve this system of equations. Yeah? You must be able to solve this system of equations. And if you can solve this system of equations and you put the solutions together as a matrix of columns, that will be your desired B. Indeed, how does matrix multiplication work? This matrix multiplies this column to give you the first column of the new matrix. This matrix multiplies the second column to give you the second column of the new matrix, and so on. And if this is 1, 0, 0, this is 0, 1, 0, 0, this is precisely the identity matrix, right? So invertibility of a matrix is simply the ability to solve a particular set of linear systems of equations. Yeah. So if you bring this to the row reduced echelon form, yeah, if it is of full rank, then what will the row reduced echelon form look like? It will be precisely the identity matrix. Okay. So the row reduced echelon form is identity if and only if the rank of A equals n. It's a square matrix, right? So meaning, and here is one more interesting fact. Again, you're supposed to know this, so I'll just state it rather than proving it. The point is, this, by the way, is if and only if BA is I. Again, this is a theorem, it needs proof, right? Now it turns out doing row operations to a matrix is the same as multiplying the matrix from the left by some other matrix. Okay. What matrix is it? I'll leave you to think about it. Okay. Doing any row operations, for example, if you want to interchange rows, that will involve multiplication from the left by a matrix, right? So in other words, if you do successively several row operations, you end up multiplying a matrix from the left by another matrix, and if the row reduced echelon form is identity, lo and behold, you have found the inverse, no less, right? So that's roughly the idea behind why this is the case. And this algorithm also tells you how to find the inverse of a matrix. You do row operations to get it to the row reduced echelon form. If the row reduced echelon form is identity, the matrix is invertible. Not only that, the matrix you have multiplied with to get identity, these row matrices, if you will, that is the inverse. So how would you find the inverse? Well, one way is to do the same row operations on the identity matrix. If A was identity, then B times A would have been equal to B itself, right? So you do exactly the same row operations needed to bring your matrix to the row reduced echelon form to the identity matrix itself, and you can recover the inverse, right? So in other words, once again, let me A n by n invertible if and only if rank is n, and that happens if and only if row reduced echelon form is identity, and A inverse is obtained by doing the same row operations to identity instead of A. Yeah? All right. So you can use these observations to calculate the inverse of a matrix on your own, just so that we are all on the same page. Yeah. And again, if you're a student of AI or machine learning, if you're a student of pure maths, this would be enough. But if you're a student of AI or machine learning, you must be able to code this up as well. For instance, I mean, it's a basic coding exercise. Yeah. Right. So now invertibility, we all know, since we've already studied linear algebra, can also be tested by calculating one single number, which is the so-called determinant of A, right? Okay, so I won't define the determinant for you, but I'll just give you some intuition as to why one would define it the way one does. If you take these columns of A, right, they form vectors, n vectors in Rn. For example, had they been in R2, they would have formed 2 vectors, right? Now the point is, if you want to be able to solve Ax equals B, the area of this parallelogram must be non-zero. Why? Because if the area is 0, then the parallelogram becomes a line, meaning the row space of that 2 by 2 matrix will be one dimensional, because one of them will be proportional to the other. That's how a parallelogram will become a line, right? And if the row space is one dimensional, we know it's not invertible. So invertibility would simply mean, in some sense, geometrically, the volume of the n dimensional parallelepiped is not 0. Yeah. So the determinant is defined to model the volume of a parallelepiped, right? I won't recall the precise definition of a determinant. It's an alternating multilinear normalized map. But more importantly, the properties of the determinant are more important. So for example, the determinant of A transpose equals the determinant of A. The determinant of AB, this is crucial, is determinant of A, determinant of B. The determinant of a so-called upper triangular matrix, what does that mean? You have the diagonal entries can be non-zero and everything here can be non-zero, but everything below the diagonal must be 0. All of these are 0. So this is an example of an upper triangular matrix. The determinant of an upper triangular matrix is simply the product of these diagonal entries. Let's call this A, this as B, etc. It's simply A times B times C, so on. It's the product of the diagonal entries. Yeah? Right. and one can compute the determinant in a recursive manner. For example, it's called, as you recall, it's called expanding along a row or a column. For example, if you decide to expand along the first row, what will you do? You'll take A11 and you'll close the first row and the first column, and you get a smaller matrix and compute the determinant of this smaller matrix, which I'll call M11. Then you take minus A12 and you close the second column and the first row, and you get a smaller matrix, which I'll call M12, and it's compute its determinant, and so on. This is the determinant. It's an recursive formula to compute the determinant, if you will. Okay. So if you know the determinants of smaller matrices, you can compute the determinants of larger matrices by expanding along rows. One more important property about determinants: if you scale a row by some number and you keep the other rows as they are, that is equal to the scaling factor times the determinant of the original matrix. If you scale the entire matrix by that number, then you pick up the scaling factor, you multiply the scaling factor with itself how many times? Equal to n times the determinant of A. So it's lambda raised to n times the determinant of A. Yeah? Right. Again, for coding purposes, by the way, while this is a very elegant and nice exercise in coding, if you wish, in C++ or whatever your favorite language is, this is the worst way to calculate a determinant. The best way is by row operations again. Okay. So notice that every time you do a row operation, so as I said, doing a row operation, what are the row operations? Interchanging rows, adding a row to a multiple of another row, and scaling a row by a non-zero number, right? Now it turns out these operations have an effect on the determinant. The determinant, if you interchange rows, then under interchange of rows, you pick up a sign. Okay, it picks up a sign. This does not change. When you add a row to a multiple of another row, this doesn't change the determinant. When you scale a row, right, this will obviously scale the determinant. Yeah? So you can use these rules to bring things to a row echelon form and compute the determinant. To put this into practice, for example, let's take this matrix. This is the same matrix that we looked at earlier. Remember the augmented matrix? I'm throwing out the last column. If I want to compute the determinant of this, remember the first operation we did was to scale the first row. But when you do the scaling business, you scale the determinant by half, right? So this is the determinant of the new matrix. Okay, sorry, this is the determinant of the new matrix by simply scaling the first row. I'm not doing any other operations yet. Then what did we do next? We cleared these two by these operations, and neither of these operations actually changes the determinant, right? So that determinant equals the determinant of 1 minus 5 divided by 2, 0, 0, half minus 1 minus 3 divided by 2, 4. Next we normalize this to 1, right? What would this do? This would again change the determinant, because twice of the determinant of this matrix would be the determinant of the new matrix. Okay. Right. Then what did we do? Maybe I'll just continue in this page. Then what did we do? Then we cleared these two entries, right? So what did we do? We did the third row to third row plus 3 by 2 times the second row, etc. These operations do not change the determinant again, so that's the same as the determinant of this new matrix. And lo and behold, what's the determinant of this matrix? It's an upper triangular matrix, so the product of the diagonal entries is the determinant. Okay? So what we originally wanted was this determinant. We scaled it by half to get this, and we scaled this by 2 to get this. So these scaling factors cancel out, and so the original determinant is indeed equal to 1. Okay? So this is a quick demonstration of how to use the row echelon form to compute determinants. Right? So we are out of time. Thank you for joining.